Hello, my name is Angelika, and welcome to my talk for the Planetary Exploration seminar. Today, I will present you with 6 rover missions. I will talk about their general structure and purpose, highlight important aspects, as well as talk about the overall design and changes across the last 5 decades of rover development. Our journey begins with the Lunokhod. Those were 2 rovers sent to the moon by the Soviet Union and the first of their kind. As you probably know, the space race in the 1960s was a competition between the US and the Soviet Union to see who would achieve milestones in spaceflight first and prove their superiority in technology and science. They were originally planned as supporting tech for a human moon mission, but then the US won the moon race and the Soviet Union focused on another milestone, and that was to control a robotic vehicle on an extraterrestrial body. For this, they planned the Lunokhod missions. Lunokhod is Russian for moonwalker. This actually started with the Lunokhod 0, whose launch pad exploded shortly after launch, resulting in a killed worker on site and radioactive polonium to be spread over a large region of today's Russia. They were very secretive, their spaceflight missions, especially their failed ones, so we only came to know about the failed rover after the fall of the Soviet Union. Which is why they presented Lunokhod 1 as the first try, which succeeded in landing on the moon in 1970. A similar build followed with the Lunokhod 2 in 1973. The Lunokhod was used to explore the lunar surface, study lunar soil, and take pictures to be sent back to Earth. It was remote controlled by 2 5-man crews in 2-hour shifts for the entire duration of the mission. The Lunokhod 1 traveled 10.5 kilometers in 11 months after losing contact with its location unknown. The Lunokhod 2 traveled 42 kilometers in 4 months when loose soil fell into the radiator and caused it to overheat. Now we get to the structure. The dimensions were 135 by 170 by 160 centimeters, and the whole thing weighed 840 kilograms. It had 8 independently powered wheels, each with their own motors and brakes. We will see this again in later designs as well. It had 2 gears, could go up to 2 kilometers per hour fast, and could overcome a step height of 40 centimeters. We have this step-like design to keep the electronics and batteries warmed by a radiator heater with polonium-210. The cover was closed during the night for additional protection and open during the day, so the solar arrays could generate energy to fuel 2 batteries inside. We have 1 directional antenna, 1 omnidirectional antenna, and 2 pin antennas to ensure communication to and from Earth. The payload included 6 cameras in total, 2 TV cameras and 4 panoramic telephotometers. The TV cameras were used for navigation to be controlled remotely by the crew on Earth. The pictures they got were black and white with less than 100 lines and 1 picture every 7 to 20 seconds. The radio signal to the moon took 3 seconds, and there was a 1-meter dead zone in front of the rover, of the Lunokhod 1, so you can imagine that steering this was not easy. The payload included the soil analyzer, containing an X-ray spectrometer, an X-ray telescope, an odometer, a penetrometer, a radiation detector, and a laser retroreflector, the latter of which was used to locate the unknown whereabouts of the Lunokhod 1 in 2010 by a NASA orbiter. This design came in handy again during the Chernobyl catastrophe. Designers were actually pulled out of retirement in 1986 to develop 2 new versions of Lunokhod in 2 weeks to help with the removal, since they were already designed to withstand radiation. Now we get to an entirely different kind of rover, still on the moon, the Lunar Roving Vehicle, also called moon buggy. The purpose of this was to assist Apollo astronauts in their scientific endeavors on the moon. In the first 3 crewed moon missions, the astronauts never steered far from their lander. As fun as the footage of these astronauts jumping around on the moon looks, navigating that was actually quite hard.
Jack Schmidt having a few problems.
Where they only had 1/6 of the gravitational forces to deal with, the spacesuits weighed more than they did, and most of that weight was in the backpack. They couldn't see their own feet, and the suits were pumped with air, making moving your fingers, arms, and legs really hard. All of this increases their metabolic rate and uses up air and water much quicker. Buzz Aldrin and Neil Armstrong never ventured further than 60 meters because of this. With the Lunar Roving Vehicle, they managed to drive 27 kilometers 4 times, climbed up mountains 30 meters tall, and ranged more than 5 kilometers from their lander. They could stay outside longer, knew their exact position at all times, and also store supplies and samples in the buggy. It was operational in total for 72 hours. There was no budget for a multi-rocket mission though, so the design restrictions were very challenging. The vehicle had to be very light and could not weigh more than 220 kilograms. It had to be able to fold up to fit into the lander and fold out with minimal intervention by the astronauts. There were some wild alternative concepts as well, such as a lunar worm, think of Dune, or a lunar motorcycle, a sort of lunar pogo stick, or a lunar flying unit powered with rockets to zoom over the moon horizontally, which, unsurprisingly, the astronauts hated. Eventually, they hired Boeing as a contractor with a more obvious choice, the buggy. Now let's talk about the design. It was 210 kilograms heavy, 2.3 by 3.0 by 1.1 meter in dimension, and could seat 2 astronauts. There were a lot of design challenges. Since the moon's surface is covered with 5 to 10 meters with lunar regolith, which is a debris layer consisting of very fine gray dust, soil, and rock fragments, with a density of only 1.5 grams per cubic centimeter, the tires had to be non-slashable and bounce over obstacles, and most importantly, not sink in. They achieved this with hand-woven mesh seal tires, again, each with their own motor, mechanically independent. There were some film and TV cameras, different types of antennas, combined with the Lunar Communications Relay Unit down here, so the rover could be steered remotely if need be. But the astronauts drove this themselves using the control and display console. The bag contained a pallet with scientific instruments, drills, shovels, and such. In order for the astronauts to help with their work, they had compartments to store their soil sample under the seats, as well as 2 silver oxide batteries. Here, I will show you a little animation that shows the rover being unfolded autonomously. We can see that the astronauts did not have to do much else besides pulling this rope. Now we're leaving the moon and entering Mars. After Lunokhod, there was no teleoperated vehicle on any extraterrestrial body until NASA landed the Sojourner Mars rover with the Mars Pathfinder lander in 1997. This mission served as a test run for the technological feasibility to control rovers in Martian environments. It was also designed to gain knowledge about the Martian environment by testing the rocky terrain and analyzing the soil for hints of past presence of water. The motto of their time was to build faster, better, cheaper spacecrafts, which they succeeded in. The development only took 3 years, $150 million for the lander, $25 million for the rover, which is cheaper and faster than any previous mission, while still managing to achieve the milestone of the very first vehicle to rover on another planet. The mission was planned to be 7 sols long, but ended up being operational for 89 sols. It was controlled via joystick, 3D goggles, and a graphical interface by 2 pilots. This was a first as well. Here you can see Brian Cooper planning out long command sequences with the 3D goggles, developed specifically for this mission. These dot arrows pinpoint the path the Sojourner should take, but it could steer autonomously and avoid obstacles with its hazard detection cameras as well. Since the time to transfer signals to Mars is too long to steer a rover in real time, they would send out long command sequences with its preferred path once a day. This is something that we'll observe in the next rovers as well. The structure is very small compared to its predecessors and successors, with dimensions of about 60 by 40 by 50 centimeters, which is about the size of a microwave. It had 6 wheels on a newly developed rocker bogie system. The details of this are handled by another presentation, so I will not go into too much detail. But basically, it has no springs, so that the wheels will always be in contact with the ground, and 2 split axes independent from each other, so that the rover can climb over obstacles twice its size. This was a new development and one that NASA favored as a standard for all future rover missions as well. It could reach speeds of 15 centimeters per second and stop for hazard detection using its cameras after every wheel turn. It traversed 106 meters during its mission without venturing any further than 10 meters from the Mars Pathfinder lander that it came on, since there had to be a clear line of sight in order to communicate with this antenna and get signals to and from Earth. It had a solar panel on top for energy during the day, but it also came with 2 non-rechargeable lithium thionyl chloride batteries for nocturnal activities and for the journey to Mars. All of this was contained in this warm electronics box. The material adherence experiment here consisted of 2 photovoltaic cell sensors with glass covers, one of which could be removed. This allowed the scientists to compare the energy conversion after one was exposed in the Martian air. There was a 0.3 efficiency reduction, independent of whether the rover was stationary or in motion, suggesting that the dust is present in the atmosphere and not raised by its movements. The payload consisted of an alpha-proton X-ray spectrometer again to determine the chemical composition of Martian soil. Now, we'll get to 2 of the biggest successes in modern space history, the Mars Exploration Rovers Spirit and Opportunity. They were twins, designed exactly the same, but sent to 2 faraway spots on Mars in 2003. The goal of the mission was of astrobiological nature, primarily to look for evidence of past presence of water. Spirit landed in the Gusev crater since satellite images suggested former hot springs due to the hints of silica, and life on Earth probably formed in hot springs. Opportunity landed in the Meridiani planet, since satellite images indicated that it might contain the mineral gray hematite, also called blueberries, which are often found near water on Earth. The mission goal was of 90 sols duration and 600-meter distance. They managed to exceed way beyond that though. Spirit got stuck in soft sand and could not be freed in 2010. It was then used as a stationary research station until losing contact in 2011. In 2014, NASA changed the mission goal so that Opportunity and Curiosity, which followed in 2012, would now be searching for evidence of life, such as the biosphere and habitable planes. Opportunity continued until 2018, when it was caught in a global dust storm. The dust settled on the solar panels and no further contact was possible. Now let's go to the structure. The dimensions are 1.5 by 2.3 by 1.6 meters, so about the size of a golf cart, and it weighed 180 kilograms in total. The top speed was 5 centimeters per second, stopping regularly for hazard detection. The structure is quite similar to what we've seen before. Again, we have a rocker bogie mobility system, a warm electronics box, and some solar panels. It also carried 2 rechargeable lithium-ion batteries. Rechargeable batteries are a first here as well, and one of the reasons for the extraordinary lifetime of these and future rovers compared to their predecessors. A radioisotope heater unit will generate 1 watts of thermal energy to the warm electronic box. We also have a UHF low and high gain antenna for communication purposes. It had 9 cameras in total, 2 panoramic cameras on a mast that could rotate 360 degrees with color filter wheels to take multi-wavelength 3D panoramic pictures in order to determine the texture, color, mineralogy, and structure of the local terrain. 2 nav cams, some hazard detection cameras in the front and the back are present as well. We also have some spectrometers to determine mineralogy of rocks and soils from a distance that are also on this mast. A new development was this rover arm that could hold several instruments like a Mössbauer spectrometer and the already known alpha particle X-ray spectrometer. There were 7 magnet arrays to collect magnetic dust particles and determine the ratio of magnetic to non-magnetic particles and composition of material in airborne dust, found by the rock abrasion tool, RAD, to remove dusty and weathered rock surfaces and expose material under it. It could drill holes and grind through hard volcanic rock. It also contained another microscopic imager to obtain close-up high-resolution images of rocks and soils, which you can think of like a combination of a microscope and CCD camera. Now we'll get to the next mission, the Curiosity rover. It was sent to Mars as a part of the Mars Science Laboratory mission in 2012. The mission duration was planned for 2 years, but it's still operational even today. Its mission goal is to investigate the Martian climate and geology, biosignatures, and planetary habitability studies for potential future crewed missions. Bigger Rovers continues with this one. It is 2.9 by 2.7 by 2.2 meters in dimension and 900 kilograms heavy, about the size of a car. The basic design and capabilities are similar to that of the Mars Exploration rovers. Here we see again a rocker bogie suspension, which was developed further to also serve as landing gear. The patterns on the wheels are analyzed by onboard cameras to determine the traverse distance. It also leaves a Morse code print in the soil that says JPL. This time there are no solar panels since they caused problems in the Mars Exploration rover missions. Instead, we have this radioisotope thermoelectric generator with plutonium-238 that is much more reliable and produces more power that was needed for the increased payload. They charge 2 lithium-ion batteries again. We also have some antennas and a heat rejection system to keep the system at operational temperatures. There are 17 cameras in total, 8 HAZ cams, 4 nav cams, 2 MES cams that rotate 360 degrees to take high-resolution pictures here. We have 1 ChemCam, which uses laser-induced breakdown spectroscopy with high-energy laser impulses to atomize and excite samples and observe it with a microimager telescope, all to gain insight into the chemical composition of rock and soil. We have RAMS, an experiment that measures humidity, pressure, temperatures, wind speeds, and ultraviolet radiation, and another robotic arm that could hold up to 5 devices and spin in a 350-degree angle for in situ experiments or sample acquisition. We have MALI, which is essentially a microscope. And we have SAM, sample analysis at Mars. Together with CAMON, they analyze powderized samples, organics, and gases. The robotic arm takes powderized samples and puts them into the opening on top of the rover. We have RAD, which detects radiation, and DAN, dynamic albedo of neutrons, to detect quantity and depth of hydrogen, ice, and water. We get into our last rover, NASA's Perseverance rover, that landed in a Jezero crater in 2020. The crater was chosen out of 60 potential landing locations that were studied for 5 years, since scientists believe it to have been flooded with water and presume there to have been a river delta a long time ago. Like Curiosity after 2014, its primary mission goal is to look for past evidence of life, specifically by studying the geological history and look for biosignatures as proof. We can see how the role of astrobiology in this mission goal has shifted over time, from it being a relatively small research field that was not taken seriously for many years, to now sustaining the most exciting missions in today's aerospace endeavors. But there is another objective this time, since Perseverance was sent to Mars along with a smaller roboter, Ingenuity. Ingenuity is a small helicopter that could be teleoperated from Earth, to show that flying in the rather thin Martian atmosphere is possible. Perseverance is still active, although Ingenuity flew its final flight in January of 2024, after its rotor blades were damaged during its 70-second flight, flying over 17 kilometers over 3 years. This time, the mission was also planned with the potential future Fetch rover in mind. While Perseverance can study rocks and soils, just like its predecessors, studying them on Earth could provide further knowledge about the Martian environment. This mission would also be necessary to achieve before any crewed missions could take place, serving as another test run to the first mission that sends humans to another planet. NASA and ESA are currently working on concept studies for that. Let's look at the design of Perseverance. As you can see, the design has been heavily influenced by Curiosity. It's 1,025 kilograms heavy and again about as big as a car. There are differences in the payload and the supporting engineering, but the entire landing system, with rocker bogie suspension and landing chassis, as well as the heat shield and descent stage, were taken almost completely from its mission before. This makes sense, since both Curiosity as well as the Mars Exploration Rovers designs were hugely successful, and reusing these designs saves money and time, as well as decreased the overall risk of failure. So the successful rocker bogie suspension system has only been modified slightly by using thicker, more durable aluminum wheels with some altered dimensions, since the Curiosity wheels have visibly deteriorated over the years. For energy, a multi-mission radioisotope thermoelectric generator that was left over as a backup part from Curiosity's construction phase now provides power, containing 4.8 kilograms of plutonium dioxide that converts heat into electricity. They fuel 2 rechargeable lithium-ion batteries. Using this over solar panels provides greater security to the rover, since it can be used during the night, during dust storms, and the winter seasons. There are again a lot of cameras, 23 in total, 7 of which for payload purposes. We have some HAZ cams, a zoomable mass cam again, nav cams, and a super cam for laser imaging similar to the setup on Curiosity. For the first time, a rover has also been equipped with a microphone to finally hear the sounds of Mars. We now know that the sounds are a bit more muted than on Earth due to the thin atmosphere. The dominant frequencies are a lot lower than on Earth. As for payload, there is another robotic arm with an instrument at its end called Sherlock, scanning habitable environments with Raman and luminescence for organics and chemicals, which hunts for sand-grain-sized particles in Martian rocks together with its partner Watson, which is a camera to take pictures of these rock textures. Sherlock will also take samples for the potential return mission. The Pixel X-ray spectrometer is a later version of the Alpha X-ray spectrometer we've encountered before. Rimfax is a subsurface radar to show hidden geological features such as hidden sand dunes, ice or lava features at least 10 meters deep. MOXIE converts Martian CO2 to oxygen. And here you can also see MEDA, the Mars Environmental Dynamics Analyzer, which is a weather station to characterize the dust size and morphology, as well as surface weather to gather information on the radiation and wind patterns on Mars. This is another leg of any potential future crewed mission, which is a refined version of the MEMS mission in Curiosity. Of course, I do not want to leave out Ingenuity, the small robotic helicopter that would be the first flying device on another planet. As mentioned, it was in operation from 2021 to 2024, flying 72 instead of the 5 initially planned times. It has a solar panel on top here, a box with sensors and cameras, a battery, and electronics for the autonomous flight control algorithms. Since the distance between Mars and Earth is so far that radio signals take between 5 to 20 minutes to travel between them, it is not possible to teleoperate a flying device in real time. Instead, it would execute flight plans sent by JPL, similar to the rovers. These antennas would communicate to Earth via Perseverance and the orbiters. The blades are made with a carbon fiber foam core, since this device had to be really light to be able to lift into the thin Martian atmosphere. These legs are also made of the material, to be super light and ensure that the helicopter lands safely. I want to close my talk with this picture of test rovers and the image of Sojourner, one of the Mars exploration rovers, and Curiosity, compared to the size of two scientists at the Jet Propulsion Laboratory. Here you can really see how big rovers have grown now. Lunokhod is a bit smaller than the Mars exploration rover, the moon buggy is similar in size as Curiosity, and Perseverance would stand right next to it. While humans have yet to journey in person to Mars, we've now sent some fascinating rovers to drive around and explore the red planet for us. Rovers are superior in many ways regarding feasibility, costs, and duration, next to crewed missions. And while populating Mars one day would certainly be interesting, rovers with their high-end technological instruments are already a huge feat for humanity, and future Mars missions, as planned by ESA with ExoMars in 2024 for example, leave us hoping to one day solve the question of extraterrestrial life.